Hello, I am Andrew Smith from the Open University Cisco Academy, and this video is the third of a series covering the modules within the Introduction to Networks, which is also part of TM257 Cisco Networking Part 1 at the Open University. In these slides today, we're actually going to be talking about rules, protocols, standards, reference models, and encapsulation. We're going to cover quite a wide range of subjects within the CCNA curricula. And what you're going to discover is that a network is a complex system where there are many rules, requirements and standards that operate at each level on each system and each technology, and it's a constantly evolving space, and it's a constantly evolving place. Basically, because networks vary in size and vary in complexity, there has to be a source and a destination to whom it sends and to whom receives. But then there will be a channel, the media or medium, depending on if it's wireless or wired, how it's being sent. And there are different standards. There's different standards for fibre than there is for copper, for unshielded twisted pair, than there are for wireless. And as some of you are aware, wireless standards are evolving as they're getting faster and scaling farther as well. So in this ever-changing landscape, we need systems that integrate. So if I were to send you something like an email from my smartphone to your personal computer, across a wireless network or across a 5G network through a fibre cabled system that might end up going through copper or whatever, through routers and switches, all at the speed of light, at the end it will end up to you in the format that I intended it to be sent. And that's why we have these different rules, requirements and standards across the entire infrastructure networking systems. It doesn't matter what device or what protocol or what message is being sent, even if it's a streamed video, that it will be sent reliably and be sent in a format that you will hopefully eventually understand at the other end of the connection as well. And we do that via communication protocols. They're basically a set of rules that enables you or your systems to be engaging each other. I mean, we have protocols as human beings, don't we? We say hello to each other. Sometimes we smile. Sometimes we make eye contact. In some cultures, it's acceptable to put our hand out and shake. For some people, it's a fist bump, and some it might be a gentle nod or bow. It's normal. We have these protocols for communication. We have these protocols for meeting and greeting and talking with each other. And the same applies here within networking as well. There has to be protocols for devices to talk to each other. We do actually talk about handshaking in networks as a way of them agreeing a communication requirement and a communication standard. And these rules will change according to the technology and the protocol that is being used. And that's where we have to ensure that there is a set of rules that are established to make that happen. And some of them are formal, as in it must work, some of them are informal, where it's negotiated based on what that technology is. And we must identify here in networking much who is the sender and receiver. Do we trust them? What is the common language? What is the speed? Because that is negotiated well, and how we confirm or act. You might hear the term act or acknowledge the communication as well. And then also you have some protocols like UDP, the user data plan protocol, that does not seek acknowledgement. It will send it, and if you get it, lucky you. Okay. And here we also talk about encoding, the zeros and ones and how they're encoded, how they're going to format, how we're going to encapsulate or wrap that data package as well, how big the packages are, timing, how quickly we're going to send them, and delivery options. Are we going to send a reply, say we have got it, or is there going to be some encoding or parity checking that's going on the way? There might even be encryption requirements or a passcode exchange as well as part of the communication. So it's very much about encoding and decoding, but not necessarily in a cybersecurity way. This is about getting it from human format to those binary zeros and ones and transmitting it across the cable. So when it's brought out at the other end, it will come back in the format we so it's there. When we talk about encoding, I mean MP3 is an encoding format. Videos for MP4 are part of a encoding standard, and there is actually a whole range of different encodings. How an image like a JPEG is sent is an encoding format as well. And when you understand that that operates at a higher layer, but we've got to push it all the way down, then send it at zeros and ones across the cable or across the wireless medium, that becomes quite important in making sure it is right and it works well and it's common across all the systems. And then when we send a message, we will define very much what is going on in the packet of information. We talk about data packets, and we'll talk about frames shortly as well, and we'll say maybe what version of communication. Is it IP version 4 or version 6? Is a flow, as in this is number 100 out of 1000. Are we going to where it's come from? So it's the source address, usually an internet protocol address, and the destination to who we're going to send it. And the classic example is often with traditional snail mail, which is becoming less common as well. And we might actually write on the letter to whom it's going, but we might also write from whom it's sent. And in the UK, if I send something by special delivery, I will have to write the postcode of my address on the special delivery docket, so they have a way of identifying where I have sent it from. Also, so they might to follow up if there is an issue. And encoding, as I've already said, is those impulses, whether it's wireless electromagnetic waves, electrical electron pulses across copper, or light pulses and signal, and we must be able to decode and encode. And it's all about sending those binary zeros and ones. That's all that's ever going to be sent in a computing system. We haven't quite got quantum yet, and it's zeros and ones, and it's got to be understandable at both ends. So whatever's been sent isn't going to come up as garbage, and we can then manage the flow and manage if we're actually going to time out. Is there no connection? It's been quiet for a few seconds. What we're going to do, and also how we manage data issues, collisions, congestion. Okay, if you have too many people on a wireless access point, what do we do? If we've got too many people on a switch network and the packets are colliding, what do we do? And how do we propagate and mitigate that and control issues on the network? Some of these issues have been mitigated over the years by different technologies. Collisions used to be more common when some of you are young enough not to know what a networked hub is, and that used to be what's called a collision domain, and switches have solved that almost totally, but now each cable point is a collision domain, so how we can then control that, and then we would try and proactively reduce the amount of issues that happen when there is data conflict on possibly a contested or congested network. We often use unicast, one-to-one communication. I can unicast now from my phone straight to my laptop and immediately send a one-to-one Bluetooth-based unicast data. Multicast is one-to-many, but it's a specific group, so that I might be multicasting an internal Teams video session, or then broadcast is sent to everybody. And it's actually a farming term. Broadcast farming was when the farmer would just broadly cast their seeds out into the field in the hope that they might land and be sowable. Okay, it's an old term, it's actually a farming term, but here broadcasts like, say, BBC Radio, it's a British example, it's being broadcast out and anybody that can connect to it will hear it. They don't care who can or can't hear it so much as there's not a specific connection, but it's broadcast equally, usually on FM or frequency modulated transmission basis. And then we talk about very much sort of nodes in network, and routers and switches are often nodes in networks, and there are different kinds of nodes. You might have concentrators, you might have routers, switches, firewalls, anything where there is a convergence point in a node and there is throughput or engagement within that space, where it's routing, moving, or redirecting or acting on traffic. So I think we can talk about protocols. There is all sorts of protocols for discovery, for engagement, and for managing traffic. You'll learn about routing protocols, where it actually decides how traffic is going to be moved around the system. You've got obviously networking protocols like IP, how traffic is going to be sent and engaged. You've got security and encryption protocols. And you will also have service discovery like CDP, Cisco Discovery Protocols, and other protocols as well. And and there are so many that can be used. Ping actually uses an old protocol called ICMP, Internet Control Messaging Protocol, that was part of a defunct routing standard, but it's still used, and it's a protocol that's used very well, or is abused equally very well, depending on what kind of actor you are within a network system. And all protocols have different functions, and they are to address all of these. Can they handle error detection? Yeah, packet loss, whether the packet's being corrupted, and they're using mathematical techniques like a cyclic redundancy check. Can we flow at an efficient rate based on the medium? Can we slow it down? Can we speed it up? And do we know who is the sender and receiver? And can we guarantee delivery? If there is an error, can we resend the packet? Which is what TCP, transmission control protocol, does. And will it work for the applications or the devices or the technologies that we're working with? And you get the examples of that, like different protocols like HTTP. It's obviously transporting web traffic. You can transport other traffic via HTTP, but it's about web traffic or web pages. TCP will be the main transport medium for the HTTP traffic, but it will use IP addressing within that. So in the wrapping, at each layer you get an IP going around a TCP, going around a HTTP, and then Ethernet, or 802.3, and you'll learn more about that, is another protocol. It is actually a data link layer encapsulation that operates on local area networks. And there is obviously the wireless standards, like 802.11, and then all the letters after it as well, which is similar to an Ethernet standard, but works according to the medium. We use Ethernet. It's an old mark. It's actually an old brand name, but we all now just use it very much interchangeably when we're talking about wired or wireless networks, or basically mainly wired networks on a switch-based system. And that means that then we have different suites of protocols, and you will come across the classic, and they're classic sort of sets of rules to interact with each other. Now, I see this and I'm really annoyed, and I do laugh at this. Apple Talk, it ain't there anymore. Apple Talk was dead 20 years ago, longer than that. Apple used TCP. Novell Network used to use, well, that's actually wrong. It's IPX-SPX. I used to be a network engineer on NetWare systems a long time ago, and that is completely legacy as well. And OSI standards quite important to understand, is a representative model. It's a logical model that is not really applied. So it was used by ISO and it's used by a lot of teachers to explain networking. And there are protocols like ISIS or intermediary systems. Intermediary system is still based upon that, but it's a legacy protocol system. And what you'll find is basically the TCP/IP suite is the one that is pretty much used in Anger or up across main systems. So you see the Novell NetWare diagram there, and I am surprised that Cisco are still using this as a slide deck. I mean, I can bore you senseless about how IPX, SPX works and how node addresses use MAC addresses, and you can actually configure your own hexadecimal addresses like D15C0, work it out, and you can do other things, but basically in that legacy sort of stack there are still, if you ignore the ISO ones that they've put there, there is still ISIS based on it, but used in TCP/IP. But all the protocols you are likely to use are within the TCP/IP suite. So there are several, they've evolved, or should I say that basically ISO and OSI are now used as a representative model, and TCP/IP is the model, is the system that you are likely, well, you are going to encounter all of the time or most of the time. And it's important to understand that TCP/IP model is representative. You can, if you're a coder, you know you can actually code your way around this, but it's there to actually describe what goes on. So the application layer is about the software and what the user uses, and the transport layer is about how you frame and control the flow of the traffic. The internet layer is about how you encapsulate, packetize, and send and receive the traffic, and then the network access is how you transport and move the traffic, whether it's wireless or wired, whether it's copper or fiber. Okay, so it does move up and down a layer, and below the Ethernet layer, that's where you've got the zeros and ones, and above the application layer, you've got us, the humans, using the technology as well. So I'm pleased that Cisco have given a great TCP/IP protocol suite example here, and it is a very good description of what goes on down at those layers, but they do miss out the fact that beneath the network access layer is the zeros and ones of the hardware being transmitted. Transport is either connection oriented with the transmission control protocol, connectionless with UDP. Connection oriented will negotiate a session and organize flow control. UDP doesn't care. It will just send it and you will receive it. And a lot of media streaming services typically use some form of UDP as well as DNS and some VoIP services as well. And also at the application layer, you're going to find a whole range of technologies. But what you will discover is that even though they've given examples of routing protocols here at the internet layer, BGP is a layer 7 application layer protocol. That slide is wrong. It actually operates on a port at the application and transport layers. It operates much higher than that, but it is often assumed that most of the routing protocols will run at the internet layer or layer 2. To manage all of this, we have a whole range of standards organisations, and in an earlier presentation I mentioned IEEE. IEEE manage the hardware standards, manage how wireless and wired networks run. Internet Engineering Task Force, you'll find stands for a lot of routing protocols, and there is a humorous one about how to send data using pigeons. Obviously, IANA looks after the IP addresses. ICANN look after the domains, and then you've got telecoms organisations as well. In the UK, Nominet will look after domains, and you'll find that there are other regional or localised standards organisations as well, such as RIPE and many others. Look them up and you will actually discover what they do and how they work with each other. But between all of them, they do collaborate, they don't compete. They might disagree sometimes, but they don't compete. And it's about how to manage the technology and the standards so that devices can communicate. It doesn't matter if you've got an Apple phone or an Android phone, whether you've got a Windows device or an Apple Mac or a Linux device, whether you've got a Cisco router or a competing router, they will all communicate equitably across the entire internet unless you have misconfigured the system accordingly. So basically, error isn't necessarily standards, it's just you as an individual setting up the system. And you can see here that basically on this slide it's already explaining what I've explained, where you can actually then set up the IP addresses and domain names for websites, and then another body looks after who gets the real world IP addresses accordingly as well. And then each of these organisations manage the hardware standards that you will have to work with within the systems. I mean, we've already talked about reference modules, so there is a little bit of repetition here. And basically, it's important to know the difference between the OSI model and the TCP/IP model, and obviously with application and presentation and session on the OSI model. Presentation is about data encoding, session is about the communication session or stream that takes place, but in TCP/IP all of that is managed in one thing. If you're a programmer, you will sometimes know that there is slight differences that you can actually handle. And here in OSI they talk about data link, and then they talk about the physical, the hardware, the zeros and ones, which is somewhat hidden in the TCP/IP model. And it is, as I say, useful to know the OSI model, but not to be ruled by it nowadays, because it is a representative model, just so you understand logically that the human's at the top and the data is at the bottom, and how you sort of would allow that stack to operate. And there are some systems that are variations on that as well. And I think I've already mentioned that it's important that we can have competitors basically have their technologies on the same network. It used to be very much a proprietary environment, but now a lot of organisations are expected to have competing products within their system, whether it's through acquisition, merger, or competitive tendering, or any of the above. And I know that certain defence organisations will have more than one device type on their infrastructure. So if one is compromised, they are not totally compromised for good strategic and defensive reasons. And I think I've pretty much covered this slide now, and I think you can see here it's very much a straightforward model to sort of explain how the system operates. And for OSI, you have to understand that here you've got these layers kind of merged into what's going on in TCP/IP. I'm not going to read all through these slides because you are capable of reading them yourself, but basically you're able to see that basically the TCP/IP model merges together some of the functions of the OSI model. And I think this slide pretty much sums up what I've been saying already anyway. My advice is to go into the curriculum and do that, investigate models, investigate traffic, and actually look at the HTTP web traffic and use the packet sniffer tool if you get the opportunity. I mean, within a network, all data is encapsulated or is segmented. We don't send a whole stream of one thing, and that's because traditionally it was unreliable. Messages would get broken up, and what we did was we multiplexed, or we broke it down into smaller segments or packets or frames. Packets is a higher layer term, frames is a lower layer term. Packets is how you divide the message, frames is how you carry a message. And a frame can actually have many packets inside, or be a set. Yeah, it could be many frames that's sending one large packet, depending on how you've configured the system. But what we're trying to do in this video you're watching, you're actually seeing it as part of many packets, and we're breaking it down into these many little segments, each with start and end bits, each with a source and destination and address, and each with contents, but also each with a mathematical parity checking or cyclic redundancy check. So TCP will sequence these packets, and we'll actually say this is packet 0, this is packet 1, this is packet 2, this is packet 3. The packet 4 turns up too early because it took a slightly different route, which it can. It will be held wait and then put back in the right place at the right time for you, and we can actually then, it becomes segmented as a PDU or a protocol datagram unit, which is the packet, and the packet will have the data, say what segment it is, and then it will have the packet header information as well as the checksums and then the bit stream, so that it can be sent off effectively. And it's basically broken down into components. So if it's lost in, well, not necessarily lost in transmission, but it can be resent, or if it's corrupted in transmission, it could be resent, or it comes out of sequence, it could be put back into sequence when the other end basically processes it accordingly. And a lot of web traffic comes like that. Have you ever noticed sometimes how different parts of a slow connected web page load differently, and then you think, yeah, it's now all been reassembled. And if you've done it a long time ago, you might have even seen some images come sort of down as a, it's hard to see, but it's just like a sort of staggered concertina effect until it all appears, or sometimes it comes as a, sort of like a slow loading all the way on. We're so used to fast connections now that most of it's instantaneous, or some browsers will not show the image until all of it has actually been loaded. And of course then it's de-encapsulated at the other end. All the header information, all of the checksum, all of the start and stop, that's just thrown away. That's just thrown away by the device or the router in some instances, and it's just put back together to sort of work for your system. We're getting near the end of these slides now, and I think we're getting to the stage where I'm covering a great deal that you've already heard. But basically, for each layer, we want to ensure that the addressing ensures that we can actually connect. IP addressing is logical and is set by the local system administrator. Data link layer is physical, and it might be in the network card. It might be Bluetooth, it might be wireless, or it might be a different interface ID according to the technology and standard. But we can, apply these accordingly. And some of you that might be astute will know that network interface cards use MAC addresses, but they can be reprogrammed or spoofed, but logically they're applied to the hardware. And if you look on your smart device, you'll see a MAC address for your Bluetooth and your wireless as well. But that way we can identify the device, or at least track that individual device on the system if it's got multiple IP addresses. We always have source and destination IP addresses from whence it came to who it's going to, but when we actually send it across a network, whether it's an IP version 4 or IP version 6 address, we always have an ID or host portion, the bit that's the actual ID of the device. And we also will have a network ID or prefix on it as well. So you often will notice, and I'll give an example here, that the 192.168.1 part of a Class C, I know it's a classic identifier, is a network portion or prefix, but the 110 is then the host portion. So that I know straight away by looking at that will separate the device IDs out accordingly. The MAC address, as I say, it should be encoded on the device or on the interface. It can be reconfigured, but basically that way we can identify the device or the interface that we're going to send it to. My laptop has got a wireless interface, it's got a wired interface, it's got a Bluetooth interface. I can actually set up other interfaces on it and actually have multiple connections. So which one am I going to send it to? And I'm going to ensure that it's the right stream for the right service for the right interface. And that way then, when it's sent across the network, the IP addresses remain consistent, but often what happens is it will change according to the hops that we're actually moving for the next hops, and that means then that we can actually track the hops that it's passing through. So this might be my local web server address, but it might be the hop of the interface of the external network ports. It might be the real world IP address that's going out on the system as well. And it's also true for the MAC addresses or the data link addresses. And it's only, you can only ever see the broadcast or the local interface addresses of your network. So what we do is we add and remove addressing information as we post it along. A bit like our delivery people, whether it's the post office or DPD, for example. Sometimes they will remove carriage load if it's gone via flight or it's gone by a truck or it's gone by a local van, so they peel it off so they know who's the next in the chain. So that they're controlling then who sends. And often you will find that you'll only ever see data link layer information for your own network, but you might see next hop information for the destination. And it's sometimes useful to run something called a trace route. You do a trace route and an IP address, you'll see the hops and the headers for the layer 3 or the networking IP addresses going on, but you'll only ever see using ARP or Address Resolution Protocol, the data link addresses for your local network or your immediate hops, which is quite important. So you will never see the destination MAC address of the web server in the distance or that router, but you will see the IP address. They know it, they're in their addressing or content tables, but you will not know it. My advice, if you are able to, is to download and install Wireshark, but I will point out, because it requires admin, some organisations will prevent this. So if it's prevented, there are packet sniffers in Packet Tracer that will emulate this activity. And what it's asking you to do is analyse ICMP or ping data. So it will actually get you to look at ping traffic. And it's useful, so if you ping www.open.ac.uk or cisco.com, it will show you the traffic, and it will show you the local MAC addresses, but not the distance ones, but it will show you a lot of the other IP address, but a lot of the discovery protocols as well. What's interesting, if you run Wireshark passively on your network, your home network, if you've got permission on the device you're using to do that, is you will discover all manner of other things and other kinds of traffic running on your system.